Welcome back. Previously, I explained the key ideas to design the MobileNetV2. So basically, there are two keys. The first is that a ReLU causes info loss when applied on low-dimensional activations. So this means that low dimensional in this context means a low number of channels, right? So ReLU preserves information only if it is applied on a high dimensional activation, that is an activation with a high number of channels. If it is applied on a low dimensional activation, then we would get an information loss. So this was the first key. The second is that the information about our images, that is information about real-world images, can be encoded in low-dimensional activations. So this information of real-world images is called, has a technical name, it's called manifold of interest. So this can be encoded, on low dimensional activations. So these are the two keys that allow to design the new block of the MobileNetV1, which is called the inverted residual with a linear bottleneck. So this is the name of the block. Okay, so now the block should take an input with a low dimension. These are the dimensions of the input, h, w times d. So the low dimensionality means that d is small. Then this block would output a low dimensional activation, h times w times d prime. So d and d prime should be small, or relatively small compared to other architectures. And the reason why they should be small is because the manifold of interest, that is the information of our real-world images, can be encoded on low-dimensional activations. So this is the new block. Now, what's inside of this block? Let me explain that on another paper, but I forgot something here. So if we have a stride that is different than 1, then these spatial dimensions should be divided by s. So similar to MobileNetV1, downsampling the data is not handled using max pooling, but rather using a strided pointwise convolution. So I'll talk about that later. So this is the block I will explain. I'll talk about the inner components of this block. Let me do that on a new page. So the input to this block is h times w times d. So as I told you, this d is small, that is the input is low dimensional, so we should not apply a ReLU directly. So what we should do is first to expand this input, they decode it into an activation with a higher number of channels, and then there is no problem if ReLU is applied. So the first layer is a pointwise convolutional layer. So the filter, the kernel used is K1 with the following dimensions. It's a pointwise, so you should have 1 by 1 by d by the number of kernels is t. So at the output we have a batch normalization, and then we apply a ReLU So here there is no problem if we apply ReLU because the data is already expanded, so the input expanded. So the input to this data here has the following dimensions. It has h times w times dt. So this is the activation that is input, the size or the dimensions of the activation that is input to ReLU. So T in the paper is the expansion factor. T is the expansion factor. Also named in the same paper, it's named the expansion rate. I don't know why they have used two different names. It was a little bit confusing, but whatever. If my memory is correct, it's called either expansion factor or expansion rate, and they found that the best value for T, except for the first layer, in all other layers of the architecture, the best value was 6. So T was equal to 6. That is, if we have an activation, we expand the number of channels by 6. If we have 3 channels, then 3 by 6 would be the number of channels. So at the output, now we have, so this is called a compression layer, a decompression layer. This is a decompression layer, decompression, or a decoding layer, or an expansion layer. Call it whatever you want. Basically expand the data so we can apply the nonlinearity. Afterwards, so the output here should have the following dimensions, should have h times w times dt. We apply a depthwise separable convolution, which is an efficient version of the convolution, of the standard convolution. So they do not use standard convolution because it's not efficient. They use depthwise separable convolution, which is the same as that used in MobileNetV2 with a minor difference that I will talk about in a moment. So in depthwise separable convolution, the first step is to apply depthwise convolution. So this is handled with a kernel. This is handled with a kernel K2 with the following dimensions. It has K times 1 times, so the number of kernels should be equal to the number of channels. It's dt. So here we should have dt. So K, in the MobileNetV2 architecture, K was equal to 3. K was equal to 3, and it's equal to 3 in most of modern CNN architectures. After that, we apply batch normalization, then ReLU. And by the way, the ReLU applied here is not the standard ReLU you know, it's ReLU 6. So ReLU 6 prevents the activations from becoming too big, and authors in MobileNetV2 found that ReLU 6 is better than ReLU when using low precision computations. I think that low precision computations in this context means that the operands are encoded on a small number of bits. Whatever. So they found that ReLU 6 works better.